Hello folks, in this video we are going to draw a force diagram for an object on an incline. Here's the scenario. A box is at rest on an incline of angle theta because friction is preventing it from sliding down the incline. We are going to draw a force diagram for the box, split that force up into components that are parallel to and perpendicular to the incline. We are going to sum the forces in the parallel and perpendicular directions, and we are going to write trig equations for the components of the forces. Let's go ahead and get started. I'm going to start by drawing my force diagram right on top of the picture to the right. Seeing the forces lined up with the picture can help us visualize what's going on. The first force we're going to draw is the downward force, the downward gravitational force that is on the box by the Earth. So writing our subscripts over here. That first subscript G means gravitational force. That'll always be the type of force. The next subscript is the feeler of the force, which in this case is the box. And the next subscript is the dealer of the force, which in this case is the Earth. There we go. What other forces do we have? Well, the box is sitting on this surface right here, and that surface is pushing into the box. And so we are going to have a normal force on that box by the surface. The word normal means perpendicular to, and so we're going to have a force from the surface that is perpendicular to the surface pushing on the box. And so we have this normal force here. It is on the box by the surface. Now the box would slide down in the absence of friction, but we do have friction here, and it's preventing that downward slide, and so this friction is pointing up the incline like that. And so we have a friction force that is exerted on the box by the surface. And those are the forces that are there. There's no ropes, so there's no tension. There's no other surfaces, so we can't have any more normal or friction forces besides the one. There's only one planet, so there's only one gravity force. And there we go. We have this picture drawn, and now we're ready to split it up into components. And I'm actually going to do it the wrong way first to illustrate what might be tempting to do based on what we've learned so far, but ultimately what won't be helpful later on. You may be tempted, this is unhelpful what I'm about to do. It's not incorrect, but it is unhelpful. You may be tempted to take our force diagram, it looks like this. We have the downward gravitational force on the box by the Earth, that angled normal force on the box by the surface, and that angled friction force on the box by the surface. Based on what we've done so far in class, you may be tempted to say the normal force has an x component to the right and a y component that's up. And the friction force has an x component to the left and a y component that's up. And you could label all those and everything, and that would be correct. It wouldn't be wrong to draw this picture. However, it's ultimately going to be unhelpful. And so I'm going to ask that you, if you're writing this down in your notebook, to circle that and put a cross through that picture. We're not going to do it that way. We're going to learn a new trick with this type of scenario that will be more helpful. And I'll draw that to the right here underneath our subscript box. So again, let's copy down our force diagram. We have the downward gravitational force on the box by the Earth, the normal force on the box by the surface, and the friction force on the box by the surface. Now here's what we're going to do. Let's actually back up for a minute. In the unhelpful picture, what we were really doing is using a coordinate system where positive x was horizontal to the right and positive y was vertical pointing up. That's a fine coordinate system. It's correct, but we can use the fact that this system is tilted to analyze this problem in a simpler way. And what we can do is we can draw our coordinate system so that it lines up with the direction of the incline. If I draw the incline into my force diagram here, that incline looks something like this dashed gray line there. And we can draw our axis, one of them parallel to the incline and one of them perpendicular to the incline. And we're going to label the direction pointing directly down the incline with the parallel symbol from geometry. And so this is the positive parallel direction. And the coordinate axis that is perpendicular to the incline, we are going to label with a positive perpendicular symbol. and this is the direction perpendicular to the incline. And we are going to draw in our components with respect to these axes rather than with respect to the horizontal x and vertical y axes. If we do that, let me grab these axes here real quick. If we overlay that directly on top of our picture, we see that the normal force only has a perpendicular component. There is no parallel component. Similarly, that friction force only has a parallel component and no perpendicular component. And so with this choice of coordinates, 2 of our 3 forces do not have components. Now, the weird thing here is that gravity will have a component, and so we'll need to break up that gravitational force into components that are perpendicular to and parallel to the incline. I'm going to start with the perpendicular component first for gravity, which will look like this, and then the parallel component of gravity, which will look like this. There we go. Those are those components, and I'll label them. We have the gravitational force on the box by the Earth. That's the perpendicular component. And we have the gravitational force on the box by the Earth. That's the parallel component. Now, let's think about what these 2 components are doing. The component of gravity that's perpendicular to the ramp is the part of gravity that's pulling the box directly into the surface. So that's the part that's squishing and crunching the surface that's there. And then the parallel component of gravity, that is the piece or the part of gravity that is actually trying to pull the box along the incline, down that incline. It's not successful because friction's present, but that's what it's trying to do. So you have the piece of gravity that's trying to pull the box down the incline, that's the parallel component, and we have the part of gravity that is crunching the surface, or that is pulling the box and crunching into the surface, and that's the perpendicular component. Now, we are all set to go. That is the only force that has components relative to these parallel and perpendicular axes. And so the next thing we want to do is write some of the forces equations. And if we do that, I'm going to do it for the x direction first. If we add up our forces, sorry, not in the x direction, we're going to go parallel direction first. So we add up our forces in the parallel direction. Let's see, we have the force of gravity on the box by the Earth, its parallel component, plus the friction force is in that parallel direction too. So the friction force on the box by the surface as well. So that's our vector equation. And if we want to write our scalar equation, so no vector arrows now, the gravitational force is pointing in the positive parallel direction, so it gets a plus sign out front. Force of gravity on the box by the Earth parallel. And then the friction force is pointing in the negative parallel direction, so it gets a minus sign. We have the force of friction on the box by the surface, and it gets a minus sign out front. So there are our sum of force, vector, and scalar equations for the parallel direction. Let's do the same thing now for the perpendicular direction. So if we add up our forces in the perpendicular direction, what do we have? Sorry, that should be an equal sign. What do we have? We have a normal force on the box by the surface. Oh, there's an N first. A normal force on the box by the surface, plus a gravitational force on the box by the Earth. And we have its perpendicular component is the component of gravity that's in the parallel direction. And if we want to write the scalar equations for this, we have a positive normal force in the perpendicular direction because it's in our positive perpendicular direction as defined by our axes. And the perpendicular component of gravity is negative according to our chosen sign convention. And there we go. Those are vector and scalar equations for the perpendicular direction. We're all set. We have one last task for today. And that last task is to write sine and cosine equations. In order to do that, we need to know which angle we're looking at. Should we consider this angle here that the gravitational force makes with its perpendicular component? Or should we consider this angle here that the gravitational force makes with its parallel component? In order to know which will be the helpful angle to consider, we want to go back to our original picture and see, are either of those two angles the angle theta we have that we make with the incline? The reason that's helpful is in the lab, usually this angle is very easy to measure. And if we can relate that angle to our force diagram, then we can use that easy to get measurement to, when we're analyzing our forces. So I'm going to now go ahead and draw in our components of gravity into this picture and label them. This is gravitational force on the box by the Earth parallel. This is gravitational force on the box by the Earth perpendicular. All right, so those are drawn in. And let's first consider this right triangle right here that I've just highlighted. Now, this right triangle has the angle theta, and it has this perpendicular here, and it has this third angle here. Let's, for sake of argument, say that theta is 25 degrees. Then this angle here must be 90 minus 25, which is 65 degrees, because 65 plus 25 plus 90 all add up to 180. So we now know that purple angle there. I want us to next consider the right angle I'm about to draw here that this component makes with that edge. So there's a right angle, and altogether that means the right angle must add to 90. This piece is 65, and that therefore the rest of the angle is 25 degrees. Now, there was nothing special about the number 25 besides I chose it for our argument here. And what that really means is the angle here that we just drew must be equivalent to the angle theta of the incline, regardless of what the angle of incline actually is. And so this angle here must be theta for any theta. If we go back to our force diagram picture down here now, we can see that the angle that's labeled in 25 degrees in the picture corresponds to this angle right here that the gravitational force makes with its perpendicular component. And so the angle theta is the angle that the gravitational force makes with its perpendicular component. A little hint here is that you should always, when you're drawing your force diagrams for inclines, go in the perpendicular direction first and then go in the parallel direction. If you do that, then you're guaranteed that the angle of incline will show up right there as the angle theta in your picture. And now that we have the angle theta for our right triangle here, we can do some sine and cosine action to figure out the components. And so let's do that. We have the sine of the angle theta is equal to opposite over hypotenuse always, and we can translate that into physics when we say the opposite side is the parallel component of gravity and the hypotenuse is the full gravitational force, which you can compute with our gravitational force law of gravitational force equals mass times gravitational field strength. Gravity equals mg. So there's our sine, and then I'm kind of running out of room on the screen, but let's go ahead and do cosine of theta up here. That's adjacent over hypotenuse. And translating that one to physics, the adjacent side of that right triangle is the perpendicular component of gravity. And the parallel side, the hypotenuse of that right triangle is the full gravitational force. And so there's our cosine equation to find the components. All right, folks, we are done now with this problem. Let's summarize real quick what we did so we can get a big picture takeaway. We drew a force diagram for this scenario here, and we broke things up into components, which is what we've been doing for a little while now. The new piece is that the components we chose to draw weren't horizontal and vertical components, but rather they were components parallel to and perpendicular to the incline. So that's really the one new piece of information, is that when doing problems on inclines, you want to break forces up into components that are parallel and perpendicular to the incline rather than x and y components. The other kind of new thing here is that if you go in the perpendicular direction first when drawing those components, then you're guaranteed that the angle theta is the angle that the perpendicular component makes with the full gravitational force. And then everything else was what we've been doing. Adding up forces in our parallel and perpendicular components, both vector and scalar equations, and doing some trigonometry to come up with our sines and cosines to figure out our components. And I just noticed in the sine equation, I wrote gravitational force BB when I should have done gravitational force on the box by the Earth. There we go. So that typo is fixed now. And there we go. That's how we do it. And then if we're doing an equilibrium problem, this sum of forces is equal to 0, and we use that fact to solve for some unknowns. I hope this is helpful. Thank you for learning with me. Thanks for taking the time to watch it, and let me know if you have any questions.